Yeah, we are pleased to have Obhik with us today. So, Obhik is coming from TIFR, where he is a postdoc right now. So, Obhik did his PhD from SINP in Calcutta, and then he went to Chalmers University in Sweden. And after that, Obhik is moving to Oklahoma State University in a few months' time. So, he'll be talking about strong clues to weak breaking, bridging collider gravitational waves and lattice studies. So, over to you, Obhik.
Thank you, Shanko, for inviting me and for the introduction. So, uh, glad to be here, and I'll be talking about uh, strong, uh, strong theories beyond the standard model as as solutions to the limitations of the standard model of particle physics. And I'll try to sort of give complementary views of probing this new hypothetical strong theories using collider studies, gravitational wave detection, and lattice gauge theory studies. So I'll show that all these can give complementary ways to probe this kind of theories. And this can be a very interesting and important uh, avenue to address several limitations of the uh, standard model of particle physics. So let me start with some introduction and motivation, but I guess this is quite trivial to this audience. Among the several outstanding issues in the standard model, I will be focusing on a few, and I will try to address this through a strongly coupled theory. So one of the major limitation is a theoretical or theoretical limitation in theoretical understanding of standard model, how the quantum field theory works in standard model. And this is called the hierarchy problem, which is essentially in one sentence, it's the issue about the stability of the electroweak scale under quantum correction. So, for example, we know that there is an electroweak scale is roughly around 100 GeV, which is sort of dictated by the mass of the W boson and also the Higgs mass. The problem is that the the mass of the Higgs boson, Higgs being an elementary scalar, so far to our understanding, is not protected by any symmetry in the sense of the 't naturalness, and that's why if let's say there are some new physics in far above the electroweak scale, which is very much possible. For example, we know that the standard model of particle physics that does not include the gravity, and there is an intrinsic scale of gravity which is at M Planck. But even before the gravity scale, even before M Planck, there can be other new physics scales. For example, let's say the scale of right-handed neutrino, or maybe the Gauss scale, or maybe the SUSY breaking scale. So there can be plenty of new physics scales, and if there are some new physics far above the electroweak scale, then the Higgs mass tries to be at that scale, because it's the nature of an elementary scalar that its mass always tries to be at the highest scale available, and because of the quantum corrections. And that's the problem which we usually call the hierarchy problem. Why the sometimes it's also called fine tuning problem. The main problem is in my opinion is that there are several scales, and Higgs particle is the mass of the Higgs is the only thing which is not protected, and so it's the only place where the so-called coarse graining of physics that does not work. So that's one challenge in standard model within our known quantum field theoretic framework, how to address this issue. And this has led to several new directions to probe into, like supersymmetry, for example. And I'll talk how a strongly coupled theory can address this issue. Now, apart from that, there are other puzzles in standard model. Uh, for example, the flavor puzzle, which is basically telling you that there is another kind of hierarchy in the mass of the matter sector, and this hierarchy is of the order of almost it's spanning around 10 to the power 5 orders of magnitude. For example, the top quark mass. The top quark is like its mass is 173 GeV, and there is no reason why it's so heavier compared to the first two generations. But this problem is probably not as severe as the hierarchy problem, because there is no connection of it with the symmetry. So symmetry, I mean, all the quark masses are perfectly fine with in the sense of Tooth naturalness, but still it's a puzzle why this peculiar flavor structure is there in the standard model. So that's another puzzle. And also there are other issues like how neutrinos can obtain mass. Then there are other problems in the, or I would say other limitations of standard model. For example, standard model really does not explain how the universe came into its current being. So how at early universe, from a electroweak preserving vacuum, how the symmetry breaking happened, and how we come into the electroweak breaking vacuum, whether it's gone through a phase transition, whether it's a fast order phase transition, or it's a crossover. In standard model, it's a crossover. So, or whether if it's a first order phase transition, whether there are associated gravitational waves, and how it's related to the baryogenesis. These are different questions that are not answered in the standard model. There's another problem which is related to the CP violation. This is also linked with the baryon asymmetry and the phase transition. So the CP violation in the QCD sector is like 10 to the 10 times suppressed compared to the CP violation in the weak sector, and there is as such no simple explanation to that within the standard model. So all of these problems, all of these limitations are there, and my idea would be to try to connect them into and try to address most of them within the framework where I introduce a new hypothetical strongly coupled theory. So I'll try to introduce you to a strong interaction, to a new strong interaction that could be the solution to many of these. So why strongly coupled theory? Why we are interested to have a strongly coupled theory? Two main things. One is that okay, we know that there is such an existing theory, and we know that theory very well. That's QCD. And also we know that it has a rich theoretical structure, which is non-abelian gauge theory, which can lead to different phases. So at high energies, it leads to free quark and gluons, while at low energy, because of the if there is an asymptotic freedom, then there is confinement, and that gives you rise to a completely different spectrum, completely different phase with hadrons and mesons, the bound states of quarks and gluons. So it's a very rich theory, and we know a lot about it because it exists in nature in the form of QCD. So what I would try to see is, let's imagine that there is so QCD is of course there, but there is a hypothetical new strong sector, and that's somehow connected to the electroweak symmetry breaking dynamics, and whether that could address some of these limitations. So I'll introduce a new hypothetical strong theory to address the limitations of standard model, and this would lead to some testable signatures at current and future experiments. Of course, that's the main motivation. And I mean, even if you don't think about all of these hierarchy problem and all this limitation, is just purely interesting because to gain deeper understanding about the strongly coupled theories, because there is a lot of things about strongly coupled theories which we still don't know, and there are non-perturbative dynamics, and it's interesting to always study this kind of theories. So now as a benchmark model, what I would introduce is something that's known as the composite Higgs model. So the idea is that all the problems are created by the Higgs boson, the elementary Higgs boson. So the main idea is we don't want an elementary Higgs boson. So we want to construct a theory at the UV without the Higgs boson. And that leads to this theory called composite Higgs model, where the Higgs boson will be realized as a composite particle at the IR. So the UV theory is a theory without any elementary scalar. There is no Higgs boson. So it's so what I will do is I'll couple the massless standard model without the Higgs to a new strongly coupled gauge theory that I'll call hypercolor, just similar to the color, which has some fermionic matter similar to quarks. I'll call them hyperquarks. So the UV Lagrangian is pretty simple. So in UV you have some of these hyperquarks which are charged under this hypercolor gauge group and the standard model gauge group with some representations, and we have the standard model quarks and leptons which are only charged under the standard model gauge group. So the UV Lagrangian is just a bunch of, at the renormalizable level, is just a bunch of gauge kinetic terms, fermion kinetic terms, and maybe some mass terms for this hyperquarks, not for the standard model quarks. Standard model is completely massless. There is no Higgs, no Yukawa coupling. Apart from that, apart from the Higgs and the Yukawa coupling, all other standard model couplings are here, and you have some additional couplings of the new strong interactions. It can have some mass, this hyperquarks, or it may not have some mass, we don't know. This mass does not play that much of a role as of now, because we can't really, we are not really sensitive to this mass scale, because what I will assume that this is a confining dynamic, so there is a confinement scale, and so these quarks and these hyperquarks are not really free. So this is at the renormalizable level. It's it's a gauge theory. So this gauge group can be some, let's say, some SUN gauge group. You can consider it some, let's say, SU4 gauge group. This will respect the gauge symmetry. Yes, just like quark terms respect gauge, quark mass can respect SU3 color. But of course, it will violate some of the flavor symmetries of this new strong theory. That's right. It will violate flavor symmetries, not the gauge symmetry. Gauge symmetry is respected. Yeah. So this is renormalizable interaction, but there can be other higher dimensional terms as well. But these higher dimensional terms are also not that many in that many are possible because of all the gauge symmetries. So you can this terms which are crossed out, you can simply ignore them because they will not be allowed by symmetries. Some of the terms are pretty important for us, and I'll elaborate on them later on. So for example, these two terms, these are 4 Fermi operators with 2 standard model fermion and 2 hyperquarks, or 1 standard model fermion and 3 hyperquarks. These 2 terms would be very, very important later on to address the flavor puzzle, to address how the top quark can get a very large mass. So watch out for this. I'll explain them later on. Then there are other terms like 4 Fermi operators with all the standard model quarks, or let's say a dipole-like operator with standard models. Yeah. No, they're different fields.
Different fields.
So hyperquarks are fields which are charged under this new gauge group and standard model gauge group. So these are some additional degrees of freedom which are not present in the standard model. They are beyond the standard model degrees of freedom. They are charged under this new gauge group and the standard model.
And how do they communicate between these two sectors?
At the renormalizable level, you see that only communication is through the gauge terms, because these are charged under gauge. They have gauge charge.
But the quarks should also have a hypercolor if they have to communicate, right? Or the
quarks don't have any hypercolor. Quarks are like our standard.
What about hyperquarks? Do they have color?
Yes, they have color.
They have color.
They have color.
They have color and hypercolor.
They have color and hypercolor, and also maybe electroid charges.
Okay.
Yeah. So at the renormalizable level, these are just yeah.
And the fermions are also distinct.
Yes.
And how you said they communicate actually?
Yeah. So at the renormalizable level, These hyperquarks are charged under, let's say, our SU3 color
Oh, okay.
and electroweak gauge group. So that's how they can communicate. But also there can be higher dimensional operators through which also they can communicate.
So the fermions transform
Under both, yes,
both.
yes, under both. This new fermions transform under both.
Both are,
Yeah.
both are good.
Yes, but our quarks, the standard model quarks, they are not transforming under this. Why these operators? Yeah, most of these are not allowed by symmetries. Either there is it's not allowed by the gauge symmetries, or maybe some symmetry of the symmetric antisymmetric combination, so it will become zero identically. Some of them will be like that. Yeah, there can be higher dimensional operators as well. Yes. Yeah, if you introduce the higher dimensional operators, of course they come with a new scale. So then it's valid only up to that scale. Yes. No. These are? These are so far bottom-up operators. Yeah. I'll make one comment about integrating out later on top down.
You still did not get the notation. So Q and L's are your quarks and leptons.
Yes.
Psi and chi are basically your hyper quarks or hyper leptons or whatever they are.
Which I combine and call it lambda, because this psi and chi, I meant two separate things which I'll introduce just.
And this, if I take f square lambda square, it is like some four Fermi interaction, which includes two hyperquarks or two hyperleptons and quarks and leptons. Okay, thanks.
So the standard model fields.
Yes.
So you are referring to this as the dipole operator?
Yeah. So this is like f bar some del mu f mu nu. This capital F is the gauge field. This is the gauge field, and this is just two. It's usual electromagnetic, or maybe the W boson standard model gauge field. Yeah, F mu nu. That's
In the usually like in the dipole kind of operators, we have this one field strength tensor and two fermions, and to make it.
So this is like f bar sigma mu nu f.
Yeah,
and
the
f mu.
Derivative won't.
Yeah, it's within the f mu nu there is a derivative. So,
okay, maybe I will ask you later. I have.
Okay, so far I just talked about the gauge symmetries, but there are also global symmetries associated with these models, and that's quite rich. So I'll talk about that soon. But before that, so in the UV, our Lagrangian is simple. So it's a standard model minus the Higgs part. Then there is a new hyperquark hypercolor sector, just like a new QCD, and some higher dimensional non-linear normalizable operators. So that's the Lagrangian in the UV.
Yeah, when you're including the higher dimensional operators, are you including only the operators because of the extra particles?
These are sort of Smith operators.
Oh, these are all Smith.
Yeah. So my notation is probably bad, so maybe I can use. So what I mean is this. So this has two fermions, one gauge field, and one derivative. So that's what my notation is. So you can think of this AF as the gauge field here. Okay, so these are sort of the Smith operators, which has only standard model fields and higher, but non-renormalizable. But then there can be others which have. Oh, yeah. Okay, so the notation is this. Magenta is standard model field, and blue is the new BSM degrees of freedom. Okay, so now, but what we want in the IR is a completely different theory. So what as we know that dimensional transmutation creates a large hierarchy of scales. So if this new hypercolor sector is asymptotically free, then it will confine at some scale, and let's say we want this confinement to be around TeV scale or few TeV scale, and so below the confinement scale, these hyperquarks, they bound together and form the bound states. So these hypermesons and hyperhadrons. And we want to identify at least one of these hypermeson to be the Higgs boson, which would be the composite particle, which would serve as the Higgs boson that we know and discovered. So this is quite in parallel with the QCD. In UV, you have some elementary fermionic degrees of freedom, hyperquarks, quarks. In the IR, you have here you have the pions as the pseudo Goldstone boson of the chiral symmetry breaking. Here we would like to have something called the Higgs boson as the pseudo Nambu-Goldstone boson of the corresponding chiral symmetry breaking in this sector. And yeah. No, there won't be one hyperhadron. There can be multiple. So there will be a tower of resonances.
But we have discovered only Higgs in that energy scale.
Right. So that would put some limits on these theories, and this would give you the opportunity to go and try to search for new resonances at the LHC and its future version. So I'll show you the predictions of what these resonances can be, what their masses can be.
So will there be any physics argument of like having only hyperhadron in this scale?
So let's say what we will assume here is that this theory confines around the TeV scale or few TeV scale. So typically our natural expectation would be that all the resonances that will come, they will be at the order of the confinement scale, so which is multi-TeV scale. But we want at least one composite object to be light, and we want to identify it with the Higgs at 125 GeV. So the way to do that is to assume that the Higgs boson is a pseudo Nambu-Goldstone boson of the chiral symmetry breaking in this sector, because as we know that pions are the pseudo Goldstone bosons in QCD, so it's direct parallel to that. So that's how you can make the Higgs boson to be even one order of magnitude lighter than the confinement scale. But other resonance, they are at the order of multi-TeV scale. So you can try to search for them, and if you don't find, you put some limits.
Thanks.
So let's now look at a bit more concrete models which can really realize this setup and give you the Higgs boson. So what are our wish list here? So the wish list is we want an anomaly-free hyperquark content that leads to asymptotically free gauge symmetry gauge theory because we want confinement, and we want a global symmetry breaking pattern. Let's say some global symmetry flavors, which is flavor symmetry, G breaking to H due to the chiral symmetry breaking. But what we really want is this unbroken part, this unbroken symmetry to have the custodial symmetry of the standard model, the SU2L cross SU2R, and the SU3 color to be a subgroup of this unbroken symmetry, which finally leads to the standard model gauge symmetry, because we in the end the low energy theory we want is the standard model. So that's really a requirement. So you have to build models such that you realize this. And we also demand that we want at least one Higgs doublet among the pseudo Nambu-Goldstone bosons of this symmetry breaking. And this requires that the hyperquarks which sort of condense to form the Higgs doublet. So this is like QQ bar condensate. So this hyperquark should not have any charge under the QCD color, because then the Higgs, if you blow up the Higgs, it will start to give you quarks and everything, right? So, but that we probably don't want. So we want at least some hyperquarks which are color neutral under our QCD. But that's not the end of the story, because this would probably solve the hierarchy problem, and you can be happy with that. But our ambition is a bit more. We also want to solve the flavor puzzle. We also want to understand how this framework can give mass to the top quark. And that requires some some additional composite fermionic states, some vector-like quarks that can mix with these standard model quarks, and this would lead to this is obtained through a framework that's called partial compositeness, and this partial compositeness requires another kind of hyperquarks which are colored because they really try to mix with the top quark. So we really want to have two kinds of hyperquarks in this new gauge sector. One is neutral under our QCD, the other is colored under our QCD. So that's what the setup is, that's what we want, this is our demand. And if we make this demand and try to see what are the minimal set of models that you can write, then this is all. These are the minimal set of models which you can write, where you have one kind of quark which is psi, which are colored singlet under QCD, and the other kind of quark, hyperquarks, which are colored under QCD. And depending on whether they are transforming under a real, pseudo-real, or a complex representation under this new gauge group, there are different kinds of symmetry breaking patterns. Typically, the symmetry breaking patterns are SUN by SON. If you have real, if these hyperquarks transform under real representation. This is SUN by SPN if they transform under pseudo-real representation, and it's like the usual QCD, SUN cross SUN by SUN diagonal if they are transforming under a complex representation. So these are all the possible minimal scenarios that you can think of, and a few things to remember here. One thing is that let's say if you look carefully here, so you will see that there are three kinds of PNGB contents are possible here, and in each of these cases you have a 2,2, which is a bidoublet under our SU2L cross SU2R, which serves as the Higgs boson. But in addition to that, there are other PNGBs as well. These are BSN scalars. These you have to search for, and this can provide some limits also to the theory. So it's a rich dynamics here. So this is one important point. The other important point, sort of prediction here, is that all of these models, you see, there is a U1. Global U1 which spontaneously breaks after the confinement. It's present everywhere in all of these models, and this U1, it's really leads to a axion-like particle which is present of the order with a mass of the order of a few GeV. That's present few GeV to few hundreds of GeV actually, so its mass is not that much bounded. So it's present in all of the models. So it's a unique prediction of all these models that you have a global U1 which is spontaneously breaking. One cautionary statement: this cannot be the QCD axion, because what we want is this theory to be confined around a few TeV scale. So if it's a QCD axion, then your model is ruled out. Then it's a visible axion. It's not. You have the kaon bounds, kaon decay bounds, and it's ruled out. So it can't be QCD axion. So it's an ALP. It can be a axion-like particle. This one, so you can produce it via gluon fusion. So it couples to the top quark. So and then decay into, let's say, diphoton, just like the axion. Yeah. So it's a ALP with all the couplings of a pure ALP you can think of. Yeah. So the only thing that we don't know is this. Is the mass of this ALP.
Yeah, but you said actually the mass is some
Yeah,
few GeV to some few hundred GeV.
This is the only thing that you cannot predict. So,
but you said actually few GeV to few hundred GeV, so that's already a prediction on the bounds, right?
Yes, so few GeV to few hundred GeV, because my symmetry breaking scale is roughly at TeV, so it cannot be beyond that. Then it makes no sense. If it's too light, then again the question comes why it's too light, and so few GeV to few hundred GeV is the ballpark range where you don't have to fine tune too much, and you are not at the sort of dangerous boundaries. So, but it's really not predictive.
Okay. Another question is actually, so you need at least two hyper flavors to have some, right? If that is actually the case, then there should be three Higgs bosons. 3 pseudoscalar Higgs bosons, right? If I just take the analogy from QCD.
No.
SU2 flavor.
So it depends on the symmetry breaking. So let's say you have two hyper. So let's
Depends on how many Goldstone bosons are put. But if you have higher SUN flavor,
Yes.
and if many of them should automatically break, it cannot be just one, I believe.
It's not just one Higgs. Yeah. So there are other Goldstone bosons also. But
which
they
will be of the order, same magnitude, right? The mass.
They will be of the order of same magnitude in the mass, but they transform in different representations under the weak gauge group. So, for example, just to give you an example, so let's say if you take this as an example, so this comes from this model here. So here you see there is a Higgs boson and there is a complete standard model singlet. But if you take, let's say, this model, then you have a Higgs boson, there is a singlet, and there is a bidoublet under SU12 cross SU2R. So you have charged Higgs and all that. So you can also look for those. And typically the bounds are not that strong that would rule out everything. So these are
the Higgs that is discovered is equivalent to a pi zero in our
exactly. It's a pi zero. Exactly. Okay. So far everything is pretty much similar to QCD, right? So everything that is there in QCD also is there. So it's just scaling up QCD in a sense. But now I will make I'll go away from QCD and introduce something else, some additional dynamics, which is really essential here. So there are two things that I will introduce. First, I will talk about partial compositeness, which I have already mentioned. I will first tell about that, and then I will introduce another concept which is called vacuum misalignment that is required for the electroic symmetry breaking. So let's start with the partial compositeness. What is this? So I told you about these operators, higher dimensional operators, and now I focus into one particular higher dimensional operator, which is one quark and three hyperquarks. It's a 4 Fermi operator with one quark and three hyperquarks. So this dimension 6, so it's suppressed by some UV scale, which can be at very high scale, let's say 10 to the power 10 or 10 to the 14 GeV, something much above any bounds can be. So this is the sort of flavor scale. And this coupling, so in the UV, this is just a 4 Fermi operator. But when you run down below the confinement scale, then these three hyperquarks, they form a bound state. And this bound state is like a baryon. So it's a fermionic bound state. So it's a vector-like under our QCD. So it's a baryon-like object. And this higher dimensional operator now, through the denormalization group running below confinement scale, it really becomes a mass mixing between the quark and this new baryon. And the strength of this mass mixing, this really depends on the anomalous dimension of this operator. So here, no, I'm not assuming SU3, but it's some SUN. I'm assuming some SU. So right, so it's not. So all of them are not charged under fundamental. So if you have fundamental and adjoint or fundamental and antisymmetric, then you can make three fermions into a singlet of the SU1, right? So they are not all of them are not fundamental. So probably I have a concrete model later. Let me see. Yes. So let's say this is one model, one concrete model. So here the gauge group is not SUN, but it's a SP4 gauge group. And the size are fundamental under SP4, while the skies are, I guess, this is antisymmetric under SP4. So these are fundamental under SP4, okay, and this is antisymmetric under SP4. The skies are antisymmetric under SP4. And now you can form a This skies do couple to the ordinary SU3 through a fundamental. Okay, so yeah, so so you can put mass to this. So they at some scale they become heavy and they decouple from the dynamics. So at very high scale you really change the SU3 running, but at low energy below TeV scale, then they're yes. Yeah, but it's a fermionic mass, so this is technically natural. It's not like a scalar mass. Okay, let me come back. Right. So here what you have done is basically you created a mass mixing between the quark and these new hyperbaryons, and the strength of this mass mixing essentially depends on the anomalous dimension. So if you have a large anomalous dimension, then the strength is very large. So mixing is very large. And if you have a small anomalous dimension for these operators, then the mixing is small. And when you further go down in energy, you have electroweak symmetry breaking, and then you have two kinds of quarks, let's say QL and TR, and they sort of couple together through the exchange of these composite resonances, and you give a mass to this to the elementary quarks through this mixing term. So the final quark mass, or standard model quark mass, is proportional to the mixing of these left-handed quarks and the right-handed quarks with these composite resonances. So heavier the mass is, the more mixing you require. Lighter the mass of the standard model quark is, the less mixing is required. So the physical states are mixture of elementary and composite degrees of freedom. First thing, and second, the third generations or the heavier generations, they are more composite, so they have a larger mixing with the composite states compared to the first two generations, which has less mixing. Now the question is, how do you determine this anomalous dimension? So that's where actually lattice study is quite important, because this is non-perturbative dynamics. You can't really predict anything just through perturbative calculations. So you really need to put these models on lattice, and then look for these operators and try to see what their anomalous dimension is. So this is sort of a ongoing work by several lattice groups, and specifically these two groups. One group works with SUN gauge theory, the other group works with SP2N gauge theories. And so far they could not put the exact models which are phenomenologically viable on lattice, but they're sort of very close to that. So that's very important. So that's where the lattice actually comes. Okay. So just to recap the idea of partial compositeness again. So at UV high scale, you have these four Fermi operators. I talked about this operator, which is the partial compositeness operator, but you could have also this sort of bilinear operator where you have two quarks and two hyperquarks. Now you run down. Below the confinement scale, this partial compositeness operator gives rise to mixing between let's say the top quark and the baryon, and this bilinear operator, so this lambda square gives rise to a Higgs, so this gives a usual you call like coupling, and this can give mass to, let's say, the lighter fermion. So now you sort of separate the mass of the third generation from the mass of the first two generations. First two generations can get mass from this bilinear, which can have lighter. So because this is a scalar operator, so its anomalous dimension cannot be that large, so it's already almost fixed, and this would give rise to lighter masses, less mixing, and this partial compositeness can give rise to a larger mixing for the third generation, and you'll with a larger anomalous dimension. And then if you go further below the electroweak scale, then you just integrate out all the baryons and everything, this tron sector entirely, and you get pure standard model and the masses of the first two generation of fermions and the third generation of fermions. So that's the story of partial compositeness. And this is the sort of state of the art of lattice studies, where this group puts multiple. So I think this is sp4 gauge group, and these are hyperquarks in the fundamental, and these are in hyperquarks in the adjoint. And these lines essentially tells you these lines are different models where you lose you are actually below the conformal window. So some of these models are viable, not all. So this is, for example, a viable model, and this sort of lies here in this picture, which is not exactly what we want phenomenologically. We want to be inside this. So lattice people are still working to put the exact models which fall within this theory region that we want, and they are hoping to give more realistic models, the results for more realistic models soon. Okay, so let's now come to the spectrum of these fermionic baryon-like states that we call top partner, because they mix with the top quark. So we call them top partner. So their spectrum is quite universal and quite predictive, although I have shown different kinds of models, but the spectrum for these top partners are universal to all of these models. And what you have is you can have these top partners with different kind of electric charge. Some of these are known. So for example, -1/3 is the electric charge corresponding to a bottom quark. So this, although the name is bad, we call it top partner, but these partners can mix with the bottom quark, and those with the charge 2/3, they can mix with the top quark. All of them are fundamental under QCD. So they can mix with our top and bottom quarks. And you see that there are multiple degenerate states around some scale, which is of the order of TeV. And some of the states are a bit heavier because they mix with our standard top or standard model bottom. So the states which mix with the standard model top or bottom, they are a little bit heavier. Then all others are quite almost degenerate, not exactly because of higher order corrections, but they are almost degenerate states. And the mass matrix has a very peculiar structure. If you put all three generations of the standard model quarks and then the spectrum of these top partners, and let's say I just want to look at the up quark sector. So it has a peculiar mass matrix where these sort of diagonal entries here, they correspond to the bilinear f square lambda square operator, and these off diagonal entries correspond to f lambda cube partial compositeness like operators. And because of this structure, what you will get is that the first two generations, they get mass of the order of electroweak wave, white times wave coupling, which comes from here. And only one generation, only the third generation receives one contribution from here, just like this, but there is additional contribution from the partial compositeness. And if the anomalous dimension of this baryons are large, then this contribution wins over this. And so the third generation has a much heavier mass compared to the first two generations. So it's very unique, very universal. It doesn't depend on what particular hyperfermions you put in, what is the global symmetry. It's always like that. Okay. So of course, these are all good, but there are also bad operators coming free with this. For example, there are operators which are 4-quark operators with all generations. So these are FCNC, and these are dangerous. But interestingly, with the partial compositeness, the interesting part is that the effective vertex is actually proportional to the mass of all of these quarks. Or the mixing. So mixing and mass, they are you can trade off one into another. So they are proportional to the mass of this quark. So it's like a Jim mechanism. So this is called well-known RS Jim mechanism. So FCNCs are really suppressed because of this RS Jim mechanism here. There are also dipole operators by exchange of these composite states, and these dipole operators, they can be dangerous. So these are a bit model dependent. If you just make a naive estimate, this will keep your fix your confinement scale to be around 50 TeV. but this is only a naive estimate. If you go into specific model, you will see that often the leading order term just cancels because of the symmetries. So in most of the models, the leading order term cancels because of symmetry, and this 50 TeV comes down to 5 TeV. So it gets a suppression of 1 by 16 pi square at the one loop order, and then you get a suppression. So in concrete setups, these strong bounds can be evaded actually. So just bottom up, you have this, but this can be evaded. So these are about the dangerous operators. So far, I started to explain the hierarchy problem, introduce this thing, talked about Higgs boson, and then change track and go into the flavor puzzle and partial compositeness. Now the question is why I should do that. So let's say I am not even bothered about this flavor puzzle. I don't want to introduce partial compositeness and all that. Without that, can I just introduce the strong sector, or can I solve the hierarchy problem? Can I think of the Higgs boson as the composite object and find all the low energy phenomenology? So let's look at that. And here we hit another point which is quite different from QCD. So let's first recap QCD. So what happens in QCD? In QCD, you have chiral symmetry breaking, and you have an unbroken diagonal SU2, which is the isospin. And electric charges, of course, electromagnetism is a subgroup of that. And in the coset space, you have the pions. You have let's say if you have two flavor QCD, then you have pi 0 and pi plus minus. How do you get a potential for these are Goldstone bosons, so they have no potential if you don't introduce any explicit breaking. So you have to introduce some explicit breaking that gives rise to the potential. And there are two origins of explicit breaking in QCD. One is just the quark masses that gives you this Gell-Mann-Oaks-Rayner relation, and this gives masses to the actually all the quarks, all the pions. So this is one source of explicit breaking. The other source of explicit breaking is electromagnetism. So electromagnetism couples only with the charged pions, and that gives a potential at one loop order to the charged pions, and this creates the famous charged pion neutral pion mass difference. So that's another source of explicit breaking. And this charged pions get masked through this Feynman diagram, which looks like this cosmic cat. It's a cartoon character of a old British cartoon. So it's a cosmic cat diagram that gives rise to this mass difference. Interesting point is that both of these masses, charged pion, neutral pion, they are positive. So they do not create a tachyonic direction. And these mass terms do not spontaneously break the electromagnetism. And that's what we really want. We don't want electromagnetism to be spontaneously broken, right? So electromagnetism remains unbroken. This just gives pure mass to the pions. And this is actually proven by Witten long back that vector-like gauge theories cannot be misaligned. You cannot break the electromagnetism in QCD and in general in any vector-like gauge theories. But the problem is that we exactly want to do that in our case. So in our case, the exact parallel is here lives the Higgs boson plus maybe other other PNGBs, and here lives the electroic symmetry, electroic gauge symmetry. So, but we want to break the electroic gauge symmetry at some stage. So if you just go by QCD, if you just introduce dynamics like QCD, you can never achieve electroic symmetry breaking. What you really want to do is you want to write a potential for the Higgs boson with a negative quadratic mass. So that creates a tachyonic direction, and that gives a vacuum expectation value of the Higgs, which will break the electroic symmetry. And this mechanism is called the vacuum misalignment mechanism, where you misalign the vacuum from this unbroken H vacuum, which is the unbroken vacuum by the strong dynamics. You want to introduce perturbations which can misalign the vacuum from this unbroken part, and that breaks some part of the gauge symmetry. So you want to do this vacuum misalignment in composite Higgs models, which is very different from QCD. And so these are the two sort of mathematical conditions to which we need to violate in order to get the vacuum misalignment. and create a tachyonic direction for the Higgs boson. So let's look at the Higgs potential in our theory. So here again, there are two terms. One term comes from the mass of these hyperquarks, which is very much similar to the quark mass term for the pions, like the Gell-Mann-Oaks-Renner. And there is a term which is given by this cosmic cat diagrams, where now instead of the photon, now you can also have the W and Z bosons running in the loop. So this gauge term and the mass term, these are very similar to QCD. This cannot misalign the vacuum because of Witten. This just gives a positive mass term. This cannot create a tachyonic direction. But there is a third term. The third term comes thanks to the partial compositeness of the top quark. So you have another term which is very much like a cosmic cat but a bit mutated. Here you have a top loop here, and this top quark term, this term is absolutely essential to create a tachyonic direction for the Higgs boson and break the electroweak symmetry. So that's why also the partial compositeness is also required to create electroweak symmetry breaking. It's not just that you are trying to introduce all this to solve only the flavor puzzle. These are too intricately tied up. So this was for a long time from when these models were introduced. It was assumed that this top quark really can do this, and there are 5-dimensional version of these models. Where the Higgs boson really lives in a bulk and all the standard model particles lives in that plane at TeV scale. And in 5-dimensional theories, it's a weak theory. It's not a strong theory. So in those RS kind of setups, you can actually compute the Higgs potential perturbatively, and you can show exactly that the top quark can really do this. And then through this ADS CFT conjectures and all that, people assume that, okay, this must be the case also in the 4-dimensional theory. So to my understanding, I think we, in 2023, we give a formal proof that, okay, really what people are assuming for a long time is actually true. It's really possible in a 4D strongly coupled theory, it's possible to misalign the vacuum through the partial compositeness term, because this leads to a quadratic term for the Higgs of this character where you have two positive definite terms with opposite sign. So there are two free parameters here, kappa 1 and kappa 2, which are the two mixing angles, and you can adjust them to get a negative sign here. So it's really possible. In the other two cases, it's not really possible. In other two cases, you will get one term with positive definite coefficient. Yes. Yeah. Yes. Yes. So this is non-real normalizable interaction. Yeah. That's a very good point. So that size can be anything, but below the confinement scale, so this leads to a mixing, right? And this mixing is determined by the strength of the mixing is determined by this anomalous dimension. So if the anomalous dimension is large, so then this gives a large contribution. So yeah. So yeah, but this comes twice, right? So that sign is that sign just cancels. Yeah. Yeah, but then the Higgs will get a CP odd structure also. Yes. Yeah. Then you can have CP.
What's in this control? There is some control.
So the controlling factor is really, I mean, if you assume that CP is preserved, if CP is violated, it's a different story. But if CP is preserved, the controlling factor is actually the anomalous dimensions of these operators with which the top quark couples. But the point is, with the other two terms, it's not at all possible to create the tachyonic direction because it's just purely positive definite. Here, at least, you have a direction where you can make it negative. So this is just a bit more details into how to prove that this would give a negative term. So let me not go into too much details, but just to tell you that once you couple these baryons with the top quark, so after the symmetry breaking, they typically comes with this just by the group theory decomposition with the Klebsch-Gordon, they couple with different couplings. And these different couplings finally gives rise to this difference between two positive definite terms. So the overall coefficient is, of course, it's undetermined, as you said, and its sign is also undetermined. There you can again, maybe you can go into lattice and you can try to study these operators, but these are probably very difficult to even study on lattice. But in principle, you can still study this and find this coefficient on lattice. But the point is, regardless of the overall sign, there is there are two terms with different signs. So it's always possible to have a negative have a tachyonic direction, regardless of the overall sign. So that's the main point here. And this coefficient you can study in principle, you can calculate in lattice. Okay, so this is fine now. So this is sort of all very formal. Now you may want to look into a particular model, a particular setup, and try to see if you can do some calculations and if you can like comment on some phenomenology. So one model which is sort of minimal in the sense that its pseudoscalar structure has one Higgs doublet and one pseudoscalar singlet. So this is the model, and this, in my opinion, is the minimal model of composite Higgs. But in the literature, if you go and search for minimal composite Higgs model, invariably you will get a model which is called SO5 by SO4. And the literature is full of that model, but let me just warn you that it's very difficult to construct a UV completion of SO5 by SO4 model in terms of a strongly coupled 4D gauge theory, because strongly coupled 4D gauge theory with fermionic matter, the global symmetry comes with SU groups, not with SO groups. So if you want to create SO groups, and then you have to do a lot of things, break things and all that. But naturally, you will get SUN by something in 4D theories. So I would say this is the minimal model, not the SO5 by SO4, although that comes with only the Higgs doublet as the PNGV. Here you have a extra singlet. So you could try to think of UV completion of this theory in terms of this 4D gauge theory, and you can have sp4 gauge group with this fermionic content, and exactly all I have said till now, they all fall into parts, except one thing that, as you asked, these higher dimensional terms, whether it's bottom up or top down. So far we talked about it as bottom up, just introduce these higher dimensional terms, and it's very difficult to UV complete the partial compositeness without adding any elementary scalar at high energy. So if you just so the holy grail is to have these 4 Fermi operators generated by some gauge dynamics. You have some gauge boson exchange, like some Z boson at very high energy, Z prime, and then you integrate that out, and then you get these 4 Fermi operators. But it's very hard, extremely difficult to get that. If you add scalars with large mass, then it's easy. You can think of some UV completion. But if someone can find such a UV completion with just a gauge boson exchange that creates these 4 Fermi operators, that would be real fantastic. You don't really need any elementary scalar. You start with only fermions and gauge bosons, gauge theories, confine, get the low energy, maybe multiple steps of confinement you require, which are called, there are also models like that called tumbling gauge theories. So you just tumble to the electroic vacuum and stop there. So, but it's not that easy to get that, unfortunately. But if you introduce some scalars, scalar mediators at high energy, then of course you will compromise with your ambition. You still introduce elementary scalars, but you can construct UV completions with that also. So one such thing we are trying to cook up, which is coming up. But anyway, so let's move with this coset, this model. So we have a Higgs and a CP odd singlet, and let's try to see if we can compute the low energy Higgs potential. So of course there are strong dynamics included, so you cannot do everything perturbatively unless you do some assumption. So we make two assumptions. One assumption is called the minimal Higgs potential hypothesis. This is just assumption that the potential is dominated by the IR contributions, which you can compute by Coleman-Weinberg potential. And the second is an additional symmetry, which is called maximal symmetry. Let's not go into the details. It's just that we introduce this just so that the potential becomes finite and fully calculable. That's it. 5 minutes. Yeah, 5 minutes. Yeah. So, in this kind of framework, the effect of the strong dynamics is captured by momentum dependent form factors. So you can write the Higgs potential, and you can compute all the terms that I have told earlier, the mass term, the gauge boson term, and the top quark term, using the Coleman-Weinberg calculation. Just only difference is that now it's your well-known Coleman-Weinberg formula, but with additional momentum dependent form factors coming from the strong dynamics with masses, these masses are the masses of the strong resonances. So you integrate them out and you get the low energy potential for the Higgs boson. And in this paper, I think we give a full analytic computation for the first time. So all previous computations are sort of assumptions where you expand the log and so on. Up to certain order, you can compute the Higgs potential, but here we just compute this fully analytically. So that's quite mathematically interesting. And then now you can go on and compute the finite temperature contribution to this potential, and including this momentum dependent form factors, which is quite different from the usual elementary theories, and you get the finite temperature potential. Interestingly, you will see that the contributions from these resonances, composite resonances, which comes around the TeV scale, they are all suppressed. They are all exponentially suppressed by e to the power minus m by t, where t is roughly at the electroic scale. So then this particular model, it leads to a first order phase transition because there is an additional CP odd particle here, so it can get a wave, and then there is a two directions where you can tunnel from this false vacuum to the true vacuum, and that generates that creates a first order transition, and this leads to gravitational wave production basically. Also, this leads to some EDM. So okay, so I'm coming to this. So if you look at the collider probes, how to probe this kind of model. So there are three kinds of probes. One is direct search of these new resonances. So these are new colored fermionic resonances. So the top partners, there are also spin 1 resonances and also different BSMP NGBs. So you can look all of these at the collider at the LHC, and the limits are roughly around 1.5 TeV. Of course, there is no discovery as of now, but the limits are kind of 1.5 TeV for these fermionic resonances, which are colored, which are the most strongest bounds around there. Then, because of the nonlinear realization of the chiral symmetry breaking, the couplings of the Higgs boson with all other standard model particles, they are also modified. So that modification, so from the precision study of Higgs couplings, you can give some limits on the scale of the symmetry breaking, scale of the confinement, which is again roughly around 1 T. So there are several works by different groups, including including some of my works where we study these things. So I'm not going into too much details now. Then one other thing, there is a strong measurement, a strong bound on the electron EDM measurements, and if there are some additional CP violations in this kind of models, which may happen if this pseudoscalar singlet gets a wave, then there are bounds on from the electron EDM as well. Although there is a flat direction here, but some of the there is a bound also in the parameter space. So these are all different kinds of probes that you can think of. In addition to that, since there can be first order phase transitions, so you can also try to look for gravitational waves, and in some regions of the parameter space, which is sort of given here, for the singlet to be lighter than the Higgs boson, you get observable, you get signals which are within the sensitivity of the future gravitational wave detectors like LISA. So it's really multiple directions complementary to each other, which can together probe this kind of strongly coupled, new strongly coupled sectors, and they are quite motivated because they can, as you can see there, they can solve multiple limitations of the standard model at one go. So some of the major references here. So these are some pioneering the first works by Kaplan and Georgi, where the partial compositeness and composite Higgs was introduced. Then the modern models were sort of written by groups, one sector of people who went to the extra dimensional way, the other people who go into the 4D way, and these are some of our contributions. So yeah, I'll just keep it here probably.